So, hey everyone, thank you all for being here today. So today I will be talking about my recent paper with Sylvain Fichet. It's called Opacity from Loops in AdS. It was actually just recently accepted into JHEP, which is really exciting. And I'm really happy to be able to tell you about it today. So looking at this title, you might immediately have two questions. First, what is opacity or opacity in AdS? And then second, why are we studying anti-de Sitter space? So I'm going to start with the latter of those two questions. Why anti-de Sitter space? And here I've listed a few reasons why you might be interested in studying theories in AdS. First, infinitely large extra dimensions are ruled out for flat space, but not in AdS, meaning that there's still this possibility of having an infinitely large extra dimension, which is still open, particularly in AdS, as pointed out by Randall and Sundrum. Theories in AdS are also dual to conformal field theories via the AdS-CFT correspondence. And then theories in AdS can be dual to strongly coupled dark sectors. Models in AdS can offer solutions to the electroweak hierarchy problem. And so there's a number of different reasons, both theoretical and phenomenological, why you might want to study or why you might want to put a theory in AdS. So in this paper, Sylvain and I set out to address the question, how do quantum dynamics affect the propagation of fields in AdS? And so we had to include the quantum corrections to the two-point function that you usually do when you do resummation. And my claim is that these quantum corrections make it so that an entire region in the bulk of AdS is opaque to propagation. And so the point of this talk is to try and not only tell you how this comes about, but also along the way try to make it seem like a reasonable conclusion. So in the first part of this talk, I'm going to be introducing the various methods we're going to use, but I'm going to introduce them in flat space. So you may have seen them before. If not, this is an okay introduction, I hope. And then in the second half of the talk, I'm going to go to AdS, talk about how opacity comes about, and talk about applications. So I'll start by introducing a really, really basic toy model, which is let's say that we have two scalars and they interact via a three-point interaction as such. So phi1 can, with this interaction of phi1 can decay into two phi2 particles if the phi1 has at least twice the mass of phi2. And this interaction will induce like quantum corrections into the two-point function that should be taken into account. And the way to do this is to sum up all of these corrections in a series. This is called resummation. And what we do is we add all the contributions to the two-point function. First, we have the bare propagator. Then we have propagation, but we put a 1pi diagram in. Then we put 2 and so on and add all of these up. A 1pi diagram is, we're going to be summing all of them, and these are any diagrams that if you cut one of the lines, the diagram remains as one diagram. It doesn't split into two. And so I've shown some examples here in the box. The one at the top left is the leading order contribution, yeah, there's higher order ones as well if we include all the contributions to the two-point function. So some terminology. This pi, I'm going to be referring to it as the self energy, and the two-point function that is the sum of this whole series, I'm going to be referring to as the dressed propagator. So this dressed propagator, as I mentioned, is equal to the bare propagator plus the corrections, G pi G, and then G pi G, pi G, and so on. Summing this up, we get this. And inserting the momentum space propagator, we get this expression for the dress propagator. So using this, I'm going to make two claims that will be useful, particularly on the AdS side. So the first is that if we, or not useful, but they'll be relevant on the AdS side. The first is that if we take the imaginary part of the self energy at leading order, so only counting that contribution from that one lowest order diagram that I've put, and then if we get this and we Fourier transform and use a narrow width type approximation, we get something that looks like this. This is an exponential suppression for time-like separations. And if we substitute in the width and then the definition of the lifetime of the particle, we get this expression, which is just the formula for like half-life of a particle that you might have first seen in like high school chemistry or something. And so the fact that this position space propagator is suppressed is just equivalent to the statement that unstable particles will decay through time. You can't have an unstable particle and have it just propagate infinitely forward in time if it can decay. And so this essentially is consistent with that view. So another way to get the same position space dressed propagator is to solve this differential equation, the Schwinger-Dyson equation for the two-point function. And I'm not going to go into too much detail showing how this works, but to prove the equivalence, what you could do is, so first of all, this D operator in front is the equation of motion operator in flat space for a scalar field theory. This would be your D squared plus M squared. And if we ignore the pi term, the term with the self energy, with the quantum corrections, then we just have dg equals minus I delta, and that is your equation of motion. If you then get this, so the solution to this differential equation will be the dress propagator, I claim. And to see this, you can write out the stress propagator as G0 plus G1 plus so on. Regroup the terms. This is not super important, but just to show you in case you're interested. Regroup the terms as follows: Fourier transform, and then insert the first equation into the second, and you find that G1 equals G0 pi G0, which is very reminiscent of that second term that I said earlier with a single 1pi insertion. So this is just a rough sketch of how the views may be equivalent. I bring this up because it turns out that it's actually easier to solve this equation in AdS than to write out a series or anything. So part 2, anti-de Sitter spacetime. So I mentioned AdS previously. Here it is a little bit in a bit more detail. So the main, the main difference with flat space is this warp factor in front. So this eta mu nu dx nu is your the Minkowski like planes that you're used to. But we can see that these Minkowski slices are scaled up and down by this this factor out in front. And so I've drawn this over on the left here, where there's these Minkowski slices, and they're scaled up or scaled down as you move through the extra dimension. They become scaled up and down. So this warp factor warps up and down the distance scales, and this includes the EFT cutoff. So an EFT cutoff you're used to thinking of as some small length scale that you can't use your theory at distances smaller than that length scale, because then you need to go to the full theory. In flat space, this corresponds to some energy scale that you can't go above. But in AdS, because these distances are warped as you move, deeper or deeper into the bulk or more out to the boundary, these distances get warped. So the EFT cutoff actually gets warped up and down if you're further in at larger z or smaller z. This will play an important role in a few minutes. So Sylvain and I, in our paper, considered effective field theory in AdS with higher dimension operators and all. Here I've written two like 3-point interactions. The first is just a vanilla 3-point interaction, and then one's kind of one's a higher dimension operator. The first thing that you may notice is the presence of this warp factor in front. So this is factors of kz that we saw in the previous slide. K is the curvature, in case I didn't mention it. So you have factors of kz that warp up and down each term. And I mentioned that the zeta is a higher dimension operator. So that is like the natural scale for this is some number, some order one, some loop factor divided by a higher mass scale, whereas lambda is not divided by that higher mass scale. And the lambda interaction is renormalizable, the zeta is not. So with these two interactions, we can form a few different loops. We can have loops where we have two lambda vertices. We can have a lambda and a zeta or two zetas. And the reason why we're doing this is we're going to end up comparing the contributions from these different loops to robustly determine, saw the chat. We're going to compare the contributions from these different loops to robustly determine where the EFT cutoff is and how that interplays with opacity. But we'll get to that in a little bit. I mentioned there is the, there we go. We're going to use the 2-point Schwinger-Dyson equation in AdS5. Here I've written the flat space version that we had before. I've indicated that with a bunch of flats. Then to go to 5-dimensional AdS space, what we do is we promote the 4s to 5s because we have an extra direction, and then we have the metric factor out in front again, and that weights the equation of motion operator, that D operator. Then I mentioned there's these Minkowski slices. So it's actually useful to Fourier transform along those slices, and then to take the Z coordinate independently. So we work in position momentum space. This is useful because the slices are each slice itself is flat, and so it's just useful to work in these coordinates. So here only the now we've gone from 5 position integrals to 1. We just have the 1 over the Z coordinate, and now it's our task to approximately solve this. So the way to do this, the way that we found to do this is via using an ansatz. To see what ansatz we might want to use, we first just look at the equation of motion, so we ignore the quantum corrections. The solution to this equation of motion is Bessel functions. At large distances, these Bessel functions go as oscillating exponentials. So we suspected that a good ansatz would be, instead of having an oscillating exponential, to have an extra function tacked on that would correspond to either a growth or a decay. And one way to look at this is if we use the imaginary part of pi, that may be reminiscent of like a damping in a simple harmonic oscillator differential equation. So it's not like too unexpected in that way. And so it turns out that when you use the ansatz, it's very much like the WKB approximation that you use in non-relativistic quantum mechanics when solving for the when you use that the semi-classical limit. Anyway, so we use the ansatz, and by calculating the contributions to the self-energy from these different diagrams, we can calculate what S should be for each of these diagrams, for each of these contributions to the self-energy. And so we went ahead and did that. The renormalizable lambda-lambda interaction gave us a log in PZ, 10 to the minus 5 times a log, times some couplings and stuff. The lambda zeta contribution gave a 10 to the minus 5 times a PZ squared. And we're looking at large PZ because this is the regime in which they're oscillating exponentials. So this lambda zeta is in general going to be larger than this lambda lambda. Then the definitely higher order contribution is this 10 to the minus 7 times PZ to the 4th. So as I mentioned, this is going to be our leading contribution. And then by comparing the size of the lambda zeta and the zeta zeta contributions, we can determine when the EFT breaks down by comparing the contributions from these two higher dimension operators. Higher dimension contributions to the self-energy. So the first step to comparing these is to write the lambda and the zeta in terms of that higher dimension mass scale that I wrote earlier. Doing that, we get S lambda zeta and S zeta zeta as such. So the question we want to answer is S order 1 possible in the EFT? So is this exponential suppression that is here, is that a real exponential suppression that will affect the physics, or is it something that is outside of the EFT? Is it something that we never really access because it's never in the exponentially suppressed regime? So to figure that out, we're going to compare the scales at which S lambda zeta becomes order 1 and at which the two contributions become of the same order. Doing the first, we get that PZ when S becomes order 1 goes as square root of lambda over K. And by comparing these two contributions, we get that this PZ goes as lambda over K. So this is the key thing, is these are different functional dependencies. So if we plot these out on a graph and use the fact that by naive dimensional analysis, lambda should be order K or larger, order pi K or larger, we find the following. So the PZ for which the propagator becomes exponentially suppressed is in red, and the PZ for which the EFT breaks down is in black. We can see that for lambda over K, not near the minimal value, the red always happens far beyond the black. So what does this mean physically? This means that if there are some particles, some scalar particles that are over here in the gray region, then they will be exponentially suppressed from propagating into the red region, which means they certainly can never make it to the black region if the red is always in front of the black, because the red region is in which the exponential suppression kicks in. So we can see that at the strongest coupling allowed at the smallest value of lambda, these two actually meet up, and at all larger values, there's always this gap between the two. So the theory, that effective field theory in AdS seems to censor itself, despite the fact that the EFT cutoff gets warped down.
Lexi, can you say something about what you're plotting on the left-hand side?
So yeah, so the left-hand side is the PZ at which the exponential suppression becomes, e to the minus order 1 in red, and then the black is the value of for momentum times the position in the extra dimension at which the EFT breaks down. And so at the strongest values of the coupling, these are near each lowest values allowed of lambda, these are the same order as each other. But as lambda gets parametrically large, there is actually this large gap, so that the position momentum propagator is always exponentially suppressed to go into this region. So this black line corresponds to the position of this, and this red line corresponds to the position of this, as shown here as well. So one is a linear function, one is a square root. So we can play with this a little bit. So imagine that instead of having infinitely large AdS, we have we truncate it by branes, and we say that particles or fields can be localized onto these branes. So say there's some red particle here, some blue here. Maybe this could be the standard model. Maybe this could be a part of the dark sector. When the standard model produces, or whatever field is on this brane produces a bulk particle with form momentum p, which p is like square root of s, because we're in the time-like region. If p is large enough, then this red region can be very close to this brane, and so the bulk particles produced can never make it over here, where maybe some part of the dark sector lives. But then as p becomes lowered, this brane moves to larger z, which is over here, larger z. And at some point, this particle is free to go over and interact with things on this brane. And so, opacity gives a mechanism it gives a mechanism to have what we call an emergent sector. So a sector that is accessible at low energies, but not at high energies. It emerges at low energies. Low values of the form momentum. This red is over here, and they can interact. At high values of the form momentum, it's here, and this cannot interact with this. And because, so some possible future directions for opacity. It's well known that at finite temperature, there is a phase transition where AdS at low temperatures goes and becomes AdS Schwarzschild with a black hole in the large Z region, which is typically the region that is opaque to propagation. And so this is well known that there is a black hole that can form here. So a natural question could be, how does opacity of this large Z region interplay with the fact that there's a black hole in the large Z region? Could opacity, kind of like cause the black hole to form at slightly higher temperatures? Could it, prevent some things from falling in if that region is opaque? And so, because Sylvain and I just recently came out with this paper, these questions we haven't gotten an answer yet, and so this is an open question. Some other future directions. So one thing I didn't mention is that although the position space dressed propagator in flat space has this exponential suppression that I mentioned has to do with particle decays of phi 1. But in AdS, except in certain cases, there are no good asymptotic states in the bulk. And so it's not so easy to connect this suppression to like a decay of some particle or something. So some sort of interplay with the AdS unitary methods that have come out recently would be interesting to study. It would also be interesting to, as I mentioned, see how this opacity effect interplays with, the AdS black hole or so on. So here's a quick summary, and if you have any questions, I'd be happy to discuss.